Okay, so welcome to a new lecture on topological vector spaces, and our primary goal in this lecture is to introduce the notion of linear mappings. But before that, let's go through a quick recall of what we have already done. Topological vector spaces. All these lectures are getting uploaded in the channel non-IITian. Now I know that you guys are already viewing it here, but still it's worthy mention of this channel. This channel is handled by my very dear friend Jyotishko, and he himself is a great, I would say, a great reader and a great, uh, I should use the term lecturer of maths. Both are students, obviously, but he has a great depth in concepts in topics in which he currently studies or he currently works independently. Um, so it's sort of fortunate in order to have this chance of uploading lectures in his channel, and he is very dedicated towards his channel as well. And in fact, I might say this, that he himself is planning to come up with lectures as well on his channel in some topics which will be extremely useful to all those who are going to view those lectures. Okay, so yeah, so without any more waste of time, let's get into it. Fine. So as we had previously discussed, what are topological vector spaces? So we just start with a vector space, and then we endo it with a topology, or the other way around, we start with a topological space, allowing us to give a vector space structure to it, in order that it follows two conditions: that all singleton sets are closed, and there exists a continuity of the operations of the vector space. That is, the addition is continuous and the scalar multiplication is continuous. And then we had a few important terminologies related to such topological vector spaces. That is, when is a set convex, when is a set balanced, what is meant by a local neighborhood. And then we proved the homeomorphism of two very important maps. One was the translation map, one was the scalar map. And due to these homeomorphisms, we had seen that it suffices to prove topological properties of local bases, local neighborhoods, in order to gain knowledge about the global topology of the space, right? And then we had defined what the interior of a set means, what the closure of a set means. We proved certain properties of those sets, and before that as well, we had also proved a very important topological property for topological vector spaces. That is, every topological vector space is Hausdorff. That is, provided two distinct points, we will always get two disjoint neighborhoods, each containing those points. Yeah, so yeah, I don't remember whether I covered this theorem in the last lecture or not, so rather let's just get into it, but I think I did it. Rather, let's just do it. So the theorem says that in a topological vector space, now to have complete clarity of what's going on in this lecture, it's advised that you guys should go and watch the previous lecture. Wait a minute. Yeah, fine. Okay, so in a topological vector space X, what do we have? Number one, every neighborhood of the origin contains a balanced neighborhood of the origin, and we have one more property which says that every convex neighborhood wait a minute, my pen tablet is causing a bit of problem. Let's see how can I fix it. Okay, I'm just wanting a bit of time. I think I can do it now. Yeah, fine. I don't think it will cause any more problem. So every convex neighborhood of the origin contains a balanced convex neighborhood of 0 of the origin. Okay. Now in some books we write the origin as theta. I prefer writing it like this, but whatever, it must be as comfortable to you. So we don't prove this. In fact, I don't even remember whether I proved it in the previous lecture or if it is done in the previous lecture, then fine. But if not, then I'm not proving it. Okay, you can just think it to be a fact in some sense, or you can rather try proving it yourself as well, because the proof is a bit complicated, to be very honest, but you can try and do it on your own. Okay. So there is basically in the first statement you just need to go through the definition of what by the definition of continuity of the scalar map, and you'll get a hold of your answer. Okay, not a problem, fine. Now this actually serves us a very important corollary, which is worth talking here. Now this exact theorem which I just stated in the here, it can be restated in this form. Okay, so let me just quote unquote, consider, or rather let me not use a quote here, it seems bad. Okay, so how can I write this? Yeah, recall that a local base is said to be balanced if its members are balanced, if its members are balanced, and it is said to be convex if its members are convex, and it is said to be convex if its members are so. Now what does our theorem say? Let me just go back. It says that every neighborhood of the origin, that means every element of some local base, because local base means the collection of all neighborhoods around the origin, some collection of the neighborhoods around the origin, it contains a balanced neighborhood of 0, right? Clear? So if it contains a balanced neighborhood of 0, I can translate this whole statement to local bases. Similarly, what does the next statement say? Every convex neighborhood of the origin contains a balanced convex neighborhood of the origin. So if I just restate this in terms of the local bases, I can state this as a corollary. I can state this as a corollary that number 1, every topological vector space has a balanced local base, because if I choose an arbitrary local base, an arbitrary collection of neighborhoods of the origin, then each of those neighborhoods will contain a balanced neighborhood. So just take the collection of all these balanced neighborhoods, you will get a balanced local base, right? Similarly, every topological vector space will have a balanced, because it's already balanced, and as well as we can re-imply the concept of a convexity as well. Okay, so rather I shouldn't talk about just topological vector space, I should say every locally convex space. That is, if I choose a space and its local base is convex, or rather if I talk about a point and I choose a local neighborhood of that point that is convex, because talking about local bases of origin and talking about local bases of an arbitrary point are basically same in a topological vector space due to the translation map. Got it? So a locally convex space has a balanced convex local base, has a balanced convex local base. If the ambient space is convex, then obviously the underlying spaces needs to be convex as well, right? You can pretty easily follow it up from the subspace or subset property of convex spaces, right? This is, in fact, these two statements are somewhat direct from the previous theorem. Fine. Okay. uh, why are they direct? So let me just state it in a very simple sense. What does the theorem say? The theorem says that if I choose an arbitrary neighborhood of the origin, I'll get a balanced neighborhood. It will contain a balanced neighborhood. So that follows from A, because if every topological vector space, if I choose its local base, then the local base will contain neighborhoods around origin. Each of those neighborhoods will contain a balanced neighborhood. Take the collection of all those balanced neighborhood, you will get a balanced local base. Okay. Now if I choose a convex local base, that is, I choose the elements inside the base to be convex, then each of those convex bases will contain a balanced convex neighborhood. Just take the collection of all those balanced convex neighborhoods, you will get a balanced convex local base. Fine. Right. Okay. Let us move on to the next important theorem, which for now completes the discussion of the set theoretic properties or the set theory topological properties of the topological vector space, as I said, for now. Okay. So the theorem is as follows, that suppose V is a neighborhood of the origin in a topological vector space, let it be named X, then the following holds. Number 1, if I has a sequence 0 less than R1 less than R2, an increasing sequence such that it is unbounded, that is Rn tends to infinity, as n tends to infinity, then I can cover X using these by just scaling V through all these scalars. Then X is exactly equal to the union equals to 1 to infinity Rn V. Okay. So what does it geometrically mean? If I talk about its geometrical sense, so suppose this is V is a neighborhood around origin, and I have a sequence of, you can think of these as radiuses. Okay, sorry, the plural of radius is radii. I am extremely sorry for my grammatical mistake, but rather if I consider each of these to be radii, then what can I do? I can just keep scaling this. So I can just scale it by R1 to get a bigger neighborhood, then by R2 to get a bigger neighborhood, and I can keep continuing this, because since these scalars are unbounded, so the radii become unbounded gradually. So I'll get at some point I'll get an infinite ball which some sort of covers the whole of X. Got it? So this is geometrical. Whenever you study topology, try to visualize the balls, or try to visualize the open sets, the metric, if there exists one, or the behavior of each of the open sets or closed sets. You will get a rather a very deep notion of what's really happening. Okay. Fine. Okay. What does statement B says? It says that every compact subset of K, every compact subset of X is bounded. So every compact subset K of X is bounded. Now it can be some sort of thought of from here as well, because if I have a compact subset, then it must be see, V is open, scaling is a continuous map, or you can think scaling is a homeomorphism, as we proved. These needs to be open, so this K must be contained in some finite union of these balls. Here is an increasing sequence, so it must be in fact contained in one of these balls, and once it's entirely contained in one of these balls, suppose this is my K, then if I go bigger from this ball, it will still be contained here, right? That's exactly the idea. That is exactly the idea. Fine. That is exactly the idea. The pen tablet is causing a lot of problem though. Whatever. Okay. Fine. Now let's go on to the next part. Okay, sorry, let me change the color. Let's go on to the next part. Let's see. Now if I choose a decreasing sequence which converges to 0, then what happens? So if I have, say, lambda 1 which is, let's say, greater than lambda 2, so on and so forth, okay, let me frame it in this way. Yeah. So if I have lambda 1 greater than lambda 2, and this sequence continues such that this sequence lambda n goes to 0 as n tends to infinity, and if V is bounded, then the collection lambda in V such that n is in the natural numbers, this set is a local base for x. Okay, clear? Okay, now let's quickly prove it. Number A. So what does it say? It says that I need to show that if I choose an increasing unbounded sequence of the scalars, then I can cover x by taking the union of the scaled neighborhood V, right? So just fix an element from capital X. Since the map alpha to alpha x is continuous by the definition of a topological vector space, okay, you can easily see that this map is basically from F to V, right? No, we chose the topological vector space to be x, right? From F to x, right? Then the set of all alpha such that alpha x in V is open. Why is it so? Recall from the recall the elementary topological definition of continuity. U is open implies F inverse U is open. So if I choose the inverse image of this set via this map, it will give me exactly the set of all these scalars alpha. V is open, right? Right, and this map is also open. This map is sorry, not open. This map is continuous, right? Okay. What more can I say? V is a neighborhood of the origin, so V contains the origin. What is the scalar which will eventually map to the origin? Alpha becomes 0, so the inverse image will contain the origin, right? Therefore, this is open, and not only open, it contains the origin. Hence, I should say contains. Now see, Rn is unbounded, so 1 over Rn for sufficiently large n is a small quantity, so it's in some neighborhood of the origin, so it must be contained here as well, right? So it hence contains this for sufficiently large n, right? Therefore, 1 over Rn with x is in V, which implies that x is in the scaled map Rn V for large n, right? So this simply implies that x is contained in this union Rn V, and from its very definition itself it must be contained here. That's trivial. So we have a both sided inclusion, right? Okay. Let us put the next statement, and the idea as I gave will be exactly the proof of the next statement as well. So I need to take a compact set inside X. So let W be a balanced neighborhood. You can always claim the existence of this. Be a balanced neighborhood of the origin such that W is contained in V, because we had proved previously that every local neighborhood will contain a balanced neighborhood. Right? That every local neighborhood of origin, every neighborhood of origin contains a balanced neighborhood of origin. So V is given to be a neighborhood of origin. I can always choose a balanced neighborhood of it, right? So let W be a balanced neighborhood of the origin. Then, by the previous proposition, K is contained in NW, right? N equals to 1 to infinity, because such sets will scale the whole of X, right? But K is compact. Since K is compact, there exists integers n1 less than n2 less than and so on and so forth till ns, such that K is contained in the union of these sets n1w union till nsw. But due to it being an increasing sequence, each of these n1w's must be contained in this nsw. So this is basically nsw, right? Clear? But then as you exceed S, K will still be contained inside nsw, right? Therefore, if T exceeds ns, then K is still contained in TW, but these TWs are contained in TVs, right? Fine. Now let's move on to the final part. What does the final part says? It says that if I have a decreasing sequence converging to 0 of these scalars and V is bounded, then we have a local base for X. Okay, using this by just scaling V using these scalars. Okay, how do we prove that? So to prove the existence of a local base, what do I need to show? Okay, let's start with the neighborhood of the origin. So let U be a neighborhood of the origin in X. If V is bounded, then there exists some S greater than 0 such that V is contained in TU for all T greater than S, right? Because T itself was also a neighborhood of the origin and it's balanced, right? So again, geometrically speaking, what is happening here is that suppose this is V, this is my V, and let's say U is like this. Okay, let me change the color, and let's say U is like this. Suppose this is my U, so I can just scale up U like this, right? So it's pretty easily visual. Okay, but now the property of the sequence lambda n, I can say that if n is so large that S times delta n is less than 1, because delta n is decreasing, the sequence of, I used lambda n, right? I didn't use delta, I used lambda n. This is a notation behavior of mine, whatever. So if S times lambda n, right, so if n is so large that S times lambda n is less than 1, because lambda n is gradually approaching 0, right? So at some point I'll obviously get a scalar S such that when I multiply lambda n with that scalar, it will eventually be less than 1, right? Then, so if I just invert out lambda n, I'll get something very large. So then V must be contained in 1 over lambda n times U by the boundedness of V, by this property, right? What does then U mean? So this means that U contains all but finitely many of these lambda n V's, right? Hence these collection U's, or rather hence this collection lambda n V's form a local base. Fine. Okay, now let's introduce the notion of a linear map. Now this introduction is obviously very evident, because when we have studied vector spaces, one of the most important criteria was linear transformations. And to be very honest, most of the study of the vector spaces, if at least I talk about finite dimensional cases, it was all linear transformations, right? We have a vector space here. We haven't yet talked about whether it's finite dimensional or infinite dimensional, which will be a topic of the next lecture. But still, the fact is that linear maps are obviously very important, and since we have a topology on it, it is obvious to talk a correlation between the linear transformations and the topological properties. Then the definition of the linear map is obviously very evident, our conventional symbol will be this for linear maps. Like in case of linear transformations, our conventional symbols was T. For linear functionals, our conventional symbol was F. Here we will use capital lambda. Definition: let X and Y be topological vector spaces over the same field in order to preserve the scalar multiplication. Then a map lambda from X to Y is called a linear map if for all x y in X and alpha beta in the underlying field F, the map evaluated at alpha x plus beta y just scales it out like this, beta times lambda y. Okay. And one more thing, let me just talk about here, like in if you recall in vector spaces, in we often use Tx as Tx. Here we will also abbreviate it to lambda x, okay, whenever we get a chance. Okay, mathematics is all about being lazy, right? Okay. Moreover, if I have a linear map from a topological vector space to its field, then we call it a linear functional. I am not writing it out explicitly, but I guess that you all should know. Okay. A quick example: the scalar map which we had studied from X to X, such that every element is mapped to alpha x, this was linear. Okay, what can you say about the translation map? Do it on your own. Check whether this translation map was linear or not. Okay, clear? Okay. Some elementary properties which are quite immediate. Some elementary properties which are quite immediate. Rather, let me now use the symbol. So yeah, I was actually going for the proof of it. So it's 0. It's 0. The linear map evaluated at the origin is just gives the origin back. Okay. Why is it so? You can just check what happens if I evaluated this. Okay. If I choose a subspace or a convex set or a balanced set, then the image under a linear map also should be so. Okay. So you can just prove it using an exercise. This is quite very extremely simple. Just go via the definition of what it means to be convex, what it means to be balanced, and what it means to be a subspace. Okay. So if A in X is a subspace, balanced set or convex set, then lambda A is so. Why? Let me just give you an idea. If it's convex, then for all x y in A, Tx plus Tx plus 1 minus Ty, this must be in A. Just apply the linear map on both sides. Okay, the T's will come out. Similarly, if B in Y is a subspace, balanced set, or a convex set, then the inverse image of it is so. Okay, let me just once just set out this notation, what this means. Okay, it's actually very trivial. F inverse B, it actually means all those elements in X such that Fx is in B. Okay, fine. Okay, now let's prove a very important, or okay, first let me define something very important as well, and this is also somewhat coming directly from the notion of vector spaces. The set X in X such that lambda x is equals to 0, which can also be thought of as the inverse map of the singleton set 0 is called the null space. Is called the null space of this map lambda. Okay, this notation will be important, as we'll see. Okay, so check whether this forms a subspace of X or not, and it will do. If you have studied linear algebra, you know that these kernels, these null spaces, they do form subspaces. Okay. Now comes a very important theorem, which again sort of correlates what our idea was when we were studying the set theoretic topology and topological vector spaces. That if I have information about the local properties of the topology, I have the information about the global properties of the topology. And the same thing we will see here as well, that if we know the property, the most important property of these linear maps locally, then we know what happens globally. So let X and Y, I am not mentioning this over and over again that there needs to be topological vector spaces over the same field, that should be quite evident. So let X and Y be topological vector spaces, and let gamma from X to Y be a linear map. Then if gamma is continuous, sorry, lambda is continuous at the origin in X, then lambda is continuous on X. In fact, it is uniformly continuous. Okay. Now this in some books this is stated as an if and only if statement, that if lambda from X to Y is lambda a linear map lambda from X to Y, it is continuous at the origin if and only if it is continuous on X. But if it is continuous on X and the origin is surely inside X, so if it is continuous on X, it must trivially be continuous at the origin. That is why I have just omitted the if and only if case, because this is what is actually important. What do I mean by it being uniformly continuous? I mean that for each neighborhood W of the origin in Y, there exists a neighborhood V of the origin in X, such that whenever Y minus X is in V, lambda Y minus lambda X is in W. Okay, so this is the definition for uniform continuity. Okay. Okay, let us quickly prove this out, and the proof is quite simple, because as we know, we can just scale out using these linear maps. Okay. So what do I do? Let W be a neighborhood of the origin in Y, then by the continuity of lambda at origin, there exists some neighborhood V of the origin such that that is contained inside W. There exists a neighborhood V of this obviously in X such that lambda mapped on V is contained in W, right. Therefore, if Y minus X is in V, then lambda Y minus X, which is nothing but lambda Y minus lambda X, this must be in W. Since lambda V is in W and Y minus X is in V, so this must be in W. So I should have written this in the reverse way. That will make it look beautiful, rather to me at least. That is, lambda evaluated at Y minus lambda evaluated at X is same as lambda evaluated at Y minus X, but Y minus X is in V and lambda V is inside W, so this must be inside W. Fine. What does this mean? Therefore, lambda maps, now these elements Y's, these come from the open neighborhoods X plus V, right, by scaling, and these elements lambda y, they come from the neighborhoods lambda x plus w by translation, not by scaling, by translation. Therefore, lambda maps the neighborhood x plus v of x, because v was the neighborhood of the origin, to lambda x plus w of or rather I should mention to the neighborhood lambda x plus w of of lambda x, right, which means that lambda is continuous at x. Fine. So, we will cover one more theorem in this lecture. We will rather give the statement of it or rather prove it. Let's just prove it. Okay. Let lambda be a linear functional on a topological vector space X. Let lambda be not identically 0, that is lambda is not a 0 map. What do I mean by this? That is lambda x is non-zero for at least some x in x. Then the following are equivalent. What are these? Number 1, lambda is continuous, the null space of lambda is closed, the null space of lambda is not dense in x, and number 4 is that lambda is bounded in some neighborhood v of the origin. Let us quickly prove this. So, first choose one to be true, let one be true. Now, so see, if lambda is continuous, now since X is a topological vector space and the field itself, you can think of it as a topological vector space, right? You can or rather, if you do not need to think of it as a topological vector space, you can at least think of the topology on it, the usual topology on the fields, the reals and the complex. We know that the singleton sets are closed, right? So, now F has 0 to be closed, lambda is continuous, this means lambda inverse of this is closed, but recall that this is exactly the definition of the null space, which implies the null space of lambda is closed. Fine. Therefore, 1 implies 2, and in fact 2 implies 3 trivially. How does this follow? Since null space of lambda is closed, so its closure is itself. This implies the closure of lambda, null space of lambda is same as the null space of lambda, and this is never equal to x. Why is it so? As lambda or rather I should write it like there exists some x in capital X such that in null space, the image of x is non-zero. So, every vector in X is not mapped to 0, therefore, the null space cannot be the whole space X, right. So, this means that the null space of lambda is not dense. Fine. So, I have proved 1 goes to 2, 2 goes to 3. Now, let us prove that 3 proves 4, and then we will go for 4 proves 1. Okay. So, 3 proves 4. Okay, and this is actually this also follows some sort of evidently, that is suppose the interior of the complement is non-empty. Okay. Then recall the theorem which said that every neighborhood contains a balanced neighborhood, every local neighborhood contains a balanced neighborhood, every convex local neighborhood contains a balanced convex local neighborhood. By local neighborhood I mean the neighborhood of the origin. Okay. Then what can I say from there? Once I have that, then I can say that therefore, for some x in capital X, some balanced neighborhood V of the origin, x plus v intersection the null space of lambda is empty, right? Okay, fine. Okay, I need a new page. Fine. Now what can I do from here? Okay, but then this is balanced in the field, therefore either it's bounded, either this is bounded or it's empty, sorry, or it's the whole of f, sorry, not it's empty, it's the whole of f, right? Now if it's bounded, we are done, then it's 4. We need to contradict this, but how can I contradict this? That is, if it is the whole field, this implies there exists some y in V such that lambda evaluated at y is same as lambda the negative of lambda evaluated at x, but that means x plus y should be inside the null space, right? But this contradicts one, contradicting the continuity of lambda, sorry, contradicting one. Fine. No, I by one I don't mean one, I mean this. So I haven't. Okay, so let this be star. So contradicting star. Okay, therefore 3 implies 4. Now 4 implies 1 is left as an exercise, is intentionally being left as an exercise. I am giving you a brief overview. Okay, try to show that lambda is continuous at the origin. Okay, how can I show this? I already have that the fourth statement is true, that is lambda is bounded in some neighborhood of V. So using that, I know that lambda x, the magnitude of lambda x as a vector, it is less than m for some positive m, x is in V. Using that, try to construct out a neighborhood of the origin which some sort of implies that lambda is continuous at origin. Okay, I think if you can try, you can go forth with it. Okay. So yeah, so this is all for this lecture. In the next lecture we will start talking about the finite dimensional spaces. So meet you guys in the next lecture.